Hello everyone. In this lessons learned video, we are going to talk about optical instruments and do some practice problems. The first question asks, what is the power of the corrective contact lens needed by a nearsighted woman whose far point is 65 centimeters? So let's draw out this situation and that of another situation. So this first one we're going to do is going to be person is nearsighted. And we will explain how that works. If the person is nearsighted, that means that they have a certain far point, which is mentioned here. Now, what exactly is the far point? The far point is the furthest that a nearsighted person can see clearly. So that means that if we have an object and it's closer to their eye than the far point, they can see it clearly here, right? But if I move it further and further away, they can still see it clearly, but then once you get to here, if you move it anywhere further than this point, they can't see it clearly. So now the object is blurry, now it's clear again, right? So that's called the far point. And so usually the problem with nearsightedness is the object is too far away, it's further away than their far point. So what we need to do is bring the image of the object to the far point. And we need to do that as a upright image. So this is the object, the actual object, and this is the image of the object. In this concept of image and object, this is from our previous chapter, and if you haven't watched that video about geometric optics, you should, because none of this will make sense without it. Right? We have the object and the image. Now, how do we do this? We use a lens. And in this case, we're using a diverging lens. So usually with these problems, we don't want to find the focal length, we want to find the power. So you might wonder what power is. Power is 1 over the focal length, but the unit for power is diopters, which is the same thing as 1 over meters. So that has to be the unit. So your focal length needs to be in meters for this to work. Now let's draw a second situation, which we will encounter later on. Let's not draw the lens for now. This is if a person is nearsighted. And nearsighted people have what's called, well, everyone does have this. They have a near point. So if you move your finger very, very close to your eye, you can try as much as you want to try to, focus on it, but your finger will still look blurry. It will not look clear. And so that's what the near point sort of does. If I have an object and it's further out from the eye than the near point, it's clear. Right? But once I move it to the near point, it's still clear. Now it's blurry. Now you can't see it. It's too close to your eye. So that's what the near point means. It's the nearest point at which the person can see clearly. So the problem usually here with near point is that the object is really close to the eye, and the person's near point is really far out. And we want to use a lens to move the image of the object to the near point upright. Okay, so the object is here, and the image formed is here. And that image is going to be formed by a lens. This time it's going to be a converging lens. Now, let's talk about some of these equations. So when you want to use this equation, you can see that the far point is basically the same thing as the distance from the image, and here the near point is the same thing as distance from the image. We always want to use the lens in a way that so that it will form an image on the person's far point or near point, because that's where they can see clearly. Right? So this is equal to the distance from image, and this is equal to distance from image. Now, where is the object, right? The object's distance from the lens, so if you were to do this, that would be the distance from the object, distance of the lens and the object. In cases of nearsightedness, that's generally going to be infinity. You might wonder why it's infinity. In the equation, that's how the objects generally act. They act as if they're infinitely far away. They're not actually infinitely far away, but you can think about it conceptually as we're trying to make it so that the lens will help us to see clearly any object no matter how far away it is from us. Right? It can be very far away, and we will still focus it and make an image of it on the far point. Now, there's also going to be the distance from the object for the nearsighted person. In these cases, it really depends on how close the person wants to be able to see clearly to them, right? So generally, it's going to be 25 for most problems. And so if a problem tells you that, you want to give the person a normal near point. Normal near point is 25 centimeters. So you want them to be able to see an object that is 25 centimeters close to them clearly. So it's generally going to be 25 most of the time. So let's move this down so we can solve this problem with space. Okay. We're told that the person's far point is 65 centimeters, so that's going to be equal to the distance from the image as well. And they want power, and we know that the objects that they're looking at are going to act as if they're infinitely far away. So we can set up this equation. Now, there's one important thing that I didn't mention. Notice how this is a diverging lens. Diverging lenses always create virtual images, and virtual images always create images whose distance from the lens is negative. So di for our diverging lens is always going to be negative. So when you plug in this value, 65, please put negative, or else it'll be wrong. So that's negative. Now I didn't fill in distance from object. It's going to be infinity, right? So I should fill that in. Infinity. 1 over infinity is 0. So 0 plus this, you will realize that focal length, the focal point of this is 65 centimeters, really negative 65 centimeters. If you convert that to meters so that we can get the power, it will be 0.65 meters, but again negative. And then for power, it's 1 over the focal length, so negative 1.538 diopters is the answer. Right, so there's a second situation here. The near point of a farsighted person is 75 centimeters. What power contact lens he must use to correct this problem and be able to read a book at a normal near point of 25 centimeters? Let's use the image we drew. This is the last time I'm going to draw this. From now on, we'll just use the equations. But I want you to get a good conceptual understanding of what the numbers mean before we just jump into using the equation only. In this scenario, the person's near point is 75 centimeters. And they want to read a book while it's 25 centimeters away. So the object or the book is 25 centimeters away, which is, we said before, in most of these problems, it's going to be like that. So if we want to find focal length, we can do this. 25 centimeters is the distance from the object. Again, we have a converging lens, but usually converging lenses do this, right? You have an object, and it will make an image that is on the back of the lens. And that image is going to be inverted. However, in this case, the focal length of our lens is really, really big because the lens kind of looks like this. It's very thin, right? So this, if you extend the circle out, this focal length is going to be really far out. And we are going to actually place the image relative to the focal length. It's going to be really, really close to the object, to the lens, right? If you do that, it'll actually form an image that is, that is over here. It actually forms a real, I guess it forms a virtual image, right? Because, yeah. So I should draw it as a virtual image, but basically it's upright and it's further back. Whole point of this is it's a virtual image once again, right? Virtual images are always upright. We want to make upright images so the person doesn't see upside down. So this DI value, again, when you use the equation here, it has to be negative. So again, negative 75. And these are centimeters. At the end, for solving for power, we have to convert these to meters. So based on this, focal length is 37.5 centimeters. Notice how it's positive, right? So the focal length is positive, but the DI is negative, right, for a nearsighted person. So the focal length is going to be 0.375 meters, and then the power is going to be, if you put 1 over 0. Okay, that's going to be the answer. 2.67 diopters, and it's positive. Okay. What power contact lens should be used to correct the vision of a farsighted person whose near point is 80 centimeters to see something clearly at a distance of 25 centimeters? Let's look at the equations and let's do a little algebra. I want to make this a little simpler. You can see that 1 over the focal length equals distance from the object, inverse of that, plus the inverse of distance from image. But you can also see that 1 over focal length is also equal to power. So we can replace this 1 over f here with power. If we do that, we will get this version of the equation. You can use this to solve the problems. I would just warn you that you need to keep in mind the signs. This is always going to be a negative value, and that the values need to be in meters so that the power answer that you get is in 1 over meters, which is diopters. So the object, they say they want to see something clearly at 25, right? So the actual object is negative 25 centimeters, but again, it has to be 0.25 meters for the units. And the image, distance from image, again, the image is always going to be formed at the near point of a person. 80 centimeters, so 0.8 meters. And actually, it should be this should be positive. I'm sorry. This should be positive. This should be negative, right? The image is negative, but the object distance is always positive. So this gives us 2.75 diopters. So this one asks for a different thing than power. They give us power already, but it says, what is the near point of a farsighted person who can read a newspaper held 25 centimeters from his eyes when he wears 3.33 diopters glasses? So the diopter, is, or the power is 3.33. The image is, we don't know the image. The distance from the image is going to be equal to the far point. In this, or the near point in this case, because the person is farsighted. And the object, again, is held 25 centimeters from his eye. So again, just like always, I should have done this. Let me redo this. The object is 25 centimeters from their eye, and the image is over here. Object is, again, going to be 0.25 meters, because we're using this equation. So the di would be equal to their near point. So the di is something like negative 1.5 meters, which seems kind of a lot. I mean, that's a really high number, but that's the value we get. Okay, so this would be, if you were to answer, in a multiple choice test, it'd probably put something like 150 centimeters, right? This negative is only for the equation. The person's near point is 150 centimeters. So if you move something closer than 150 centimeters to their eye, they can't see clearly. So you can see how that disruptive that can be. So they really need corrective lenses in that case. Here we're talking about a magnifying glass. So the focal length of a magnifying glass is 15 centimeters. If the near point of a person is 25 centimeters, what is the magnification of this glass for this person when his eyes are focused at infinity? So these magnifying glass problems, they ask for magnification, but it's not the same type of magnification that we've talked about before. In this case, and by before I mean the geometric optics chapter, it's going to be a little different. The magnifying glass is going to be, the magnification of it is going to be equal to the near point of the individual, right, over the focal length of the glass. Now, this would apply if the person has relaxed vision. And relaxed vision is the same thing as, their eyes are focused in infinity. Eyes focused in infinity, which is the case in this problem, right? They say their eyes are focused in infinity. If the person is using strained vision, right, then it's going to be the exact same formula except you add a 1 to the magnification at the end. So this is strained vision. Right, this is if you were to move your finger kind of close to your eye and try to focus on it, right? As opposed to just looking at it relaxed. If you consciously try to focus on it, that's called strained vision. And if you just look at it and it looks blurry to you and you don't care, that's called relaxed vision. All right. So if you move your finger kind of not too close to your eye, but kind of close, it'll get blurry. But then if you really focus on it consciously, you'll be using strained vision. In this case, we use relaxed vision, right? Because that's what the problem gives us. So the near point of the person is 25 centimeters. And the focal length of the magnifying glass is 15 centimeters. So this comes out to very easy problem, 1.67 as the magnification.